Chapter 27 is about our two-sample test. In our last video, we introduced the two-sample test. Now we're going to talk a little bit about when we can use the two-sample test, as well as do a few practice problems. So first, when can we use our two-sample z-test? So we said that we could use the two-sample z-test if we have two independent, simple, random samples. Now remember, independent samples means that the two samples are in no way related. They do not affect each other in any way. Independent means not related, don't affect each other. And we are supposed to have simple random samples. Most of what we do in this class, all of our formulas are for simple random samples. And we use this test to determine if our two population averages are equal or not, or also less than or greater than. We can also use this test, so we can use the exact same computations if we have a controlled experiment. Now, if you don't remember what experiments are, you can go back to chapter 2. You can also read section 3 in this chapter, chapter 27, for more details. But if we have a controlled experiment where we simply randomize the subjects into two groups, and we want to see if any treatment was effective or not, we can use this two-sample z-test. But the important thing here is that we can't use the two-sample z-test for dependent samples. So here are some examples of dependent samples. So for example, 275, let's say we want to compare the repair costs of moderately damaged cars at two different garages. And we want to see if garage 1 charges customers less to repair their cars than garage 2 does. Well, we could perhaps randomly select 10 damaged cars and take each car to both garages. And if we did that, we would have the repair costs at each garage are obtained for the same cars. And that way, it's not seeming like one garage is more expensive just because they happen to get more heavily damaged cars, because each garage looked at the same cars. And so any true differences in the garage costs wouldn't be concealed by just the severity of the damage to the cars. Now these would be dependent samples since the same car is in both samples. And we would have to use different formulas to compare the groups. Now let's just make a note here that this would be a very good design for an experiment. We just need to use different formulas and not the z-test. Okay, so once again, it is a very good design. There's nothing wrong with doing it this way. You just need different formulas and not the z-test. So we're not actually going to learn in this class what you would use to evaluate it. So we can't use it for dependent samples. We also can't use it for matched pairs. So matched pairs is something where, so like in our first example, we sent the same car to both garages. If there's something where you can't actually do both treatments to the same person, then you can do what we call matched pairs. So in this study, we want to see if the psychological environment affects the anatomy of the brain. And so Mark conducted a study on rats. He used many litters of rats. From each litter, he selected one rat at random for the treatment group and one for the control group. And this is an example of matched pairs. Since each pair came from the same litter, they should be alike in many ways. And this helps the two samples be very similar. And matched pairs are a very effective way to compare groups. So it's a very good way to do experiments. But the groups are not independent because each group is related because the rats were in matched pairs. And so we'd have to use different formulas to compare the groups. So for each of these examples, we're going to go through and try and figure out whether or not we could use the two-sample z-test. Basically, we're asking, are the groups independent? So number 1, a geography test was given to a simple random sample of 250 high school students. Students were asked to identify Great Britain and France on a map. As it turned out, 65.6 could find France compared to 70.4 for Great Britain. And is this difference statistically significant? Okay, so first, could we use a z-test here? Well, we asked the same students both questions. So each student was in both groups. So the groups are not independent. So we cannot use the two-sample z-test. So for our next one, a psychologist develops a test that measures social insight. She gives the test to a random sample of female students and a random sample of male students. She then compares the average scores for the two groups. Now this one, notice how there's two different groups. We have a random group of female students, a random group of male students. I don't see any way that these students are related, and so this would be two independent samples. So two independent groups, so we could use the two-sample z-test. Now in problem 3, a math professor wants to know whether big classes or small classes work better. He teaches a small class in fall quarter, 40 students, and a large class in spring quarter, 120 students. Final exams show that the fall average, so we have the fall average and standard deviation, spring average and standard deviation. And the question is, should he test the hypothesis that the small classes are better? And so this one is kind of a trick example because when you look at it, those two classes should be independent, right? Those two classes shouldn't be related at all, so they are independent groups, which is good, but here's the problem. Notice how he just teaches one class and looks at all their data, and he teaches the other class and looks at all their data. And so that means that these are not randomly chosen. Instead, they were convenient samples. Convenient because he was already teaching in class, he just took their data, it was very convenient. And this part is bad. So remember, we're supposed to do independent, simple, random samples, and these aren't random samples. Since they're not random samples, we cannot use the two-sample z-test. Now number 4, a large company is interested in computing or comparing whether the employees in sales or management are happier with their jobs. They take a random sample of 75 sales employees and find that 88% are happy. They take a random sample of 75 management employees and find that 91% of them are happy. Is there evidence of a difference between the two groups? Well, let's see. There's two different samples. They're both random. I don't see any reason they should be related. So this would be independent and random samples. So we can use the two-sample z-test. Now technically, if you were paying lots of attention, notice that those weren't averages, those were percentages. And so we would use the two-sample z-test for percentages, which we haven't actually learned yet. But there is one, and it is in your textbook. You can look it up if you want. Okay, number 5. To determine whether the average GPA of male USU students is equal to the average GPA of female USU students, a researcher finds the average and standard deviation of all the female USU students and all the male USU students. If we had these numbers, could we perform a hypothesis test to decide whether the average GPA of male USU students is equal to the average GPA of female USU students? If not, what could we do? So this is kind of another trick one because notice these words all. So this means they actually took the data for the population. So they actually have the data for the population of all the students. so not a sample. So we don't use hypothesis tests when we have the population data, because it doesn't make sense. It's redundant. You already know the population data. So instead, just compare the average GPA of all females and all males, since you have that data. So basically, you don't need a hypothesis test if you already have the population data. And number 6, does regular physical therapy help lower back pain? An experiment is conducted and randomly assigns patients with lower back pain to 2 groups, a treatment group and a control group. Over a 5-week period, both groups receive regular examination and advice. The treatment group also gets bi-weekly physical therapy. At the conclusion of the experiment, the level of improvement is compared for both groups. Let's see. So we are randomly assigned to groups. That's a good sign. I don't see any reason that these 2 groups are related, so these would be independent groups. So yes, we can use the 2 sample z-test. And number 7, a researcher wants to test the drug to see if it's effective at reducing blood pressure. He sampled the blood pressure of the same people before and after they received a dose. So this one, we only have 1 group and we measure them twice. So this is kind of that matched, well, it's not exactly matched pairs because it's the same person, but we're doing it twice. So these are not 2 independent groups. So we cannot use the 2 sample z-test. But it is a good experiment design. It's a very good way to see if the drug is actually effective or not if you measure the same people twice. You just have to use different formulas. So that was, once again, just practice at seeing when the 2 sample tests would be appropriate. At this point now we're just going to practice several problems. So example 276, we'd like to assess the effect of piano lessons on spatial temporal reasoning by comparing the average change in the reasoning score of pre-kindergartners who received piano lessons for 6 months to the average change in reasoning score of a control group that did not receive piano lessons. There were 34 students in the piano lesson group. The average score was 3.62, standard deviation of 3.06. 44 students in the control group. Average score was 0.39, standard deviation of 2.42. So we have the piano and control. Now, obviously, when you look at this, the piano group was scoring higher, but the question we're wondering is that difference just due to our chance error, or is this difference so big that we think the piano lessons were really making a difference? Now, technically, you should check to see if you could do this test. So, are both groups have big sample sizes, or are they normally distributed? Well, both of our sample sizes are bigger than 30, so we can do this test. So, for our null hypothesis would be that the average change should be the same for both groups. The alternative would be that the average for the piano group is higher than the average for the control group. Now, you do need to put in here either the word all or the word population, so I know you're talking about the population and not just a sample. So let's say the population average should be the same for both groups. And the alternative is that the population average for the piano group is higher than the population average for the control group. Now one of our intermediate steps is we need to find both standard errors. So standard error for piano is going to be the SD over the square root of the sample size. And their SD was 3.06 over the square root of the sample size, which was 34. So 0.52. And the SE for the control is going to be their SD of 2.42 over their sample size of 44. So 0.36. Now Z, our test statistic, is going to be the sample average for piano, since I'm doing piano first in all of this, minus the sample average for the control over the square root. We're going to do standard error for piano squared plus the standard error for the control group squared. So the sample average for piano was 3.62. Sample average for the control was 0.39. And the two standard errors were 0.52 and 0.36. And we square both of those and add them together. And this gives me 5.13. Now my p-value, we have to figure out which direction we want to shade. And once again, remember, this is kind of the hardest part sometimes. So we did piano minus control. Now according to our alternative hypothesis, we think the piano group should be higher, and so this should be big numbers minus small numbers. So that should give me a positive result, which means I should shade to the right. And once again, I'm going to use that logic every time to try and figure out which direction to shade. So here's my Z equals 5.13, and I want to shade to the right. So I pull up my normal table. I want Z equals 5.13. So as I continue on my table, 5.13 would be down here. Continue on the pattern. This would be about 100. So the area to the left is about 100. So the area to the right is about 0. So my p-value is about 0. That is a small p-value because it's smaller than 5%. So I will reject the null hypothesis. And we can write our conclusion. So we have, now that's a really small p-value, so I have lots of evidence. We have lots of evidence that the average scores of all the piano students would be higher than the average scores for all the non-piano students. And hence you could conclude that the piano was helping. So for 277, 100 freshman women and 81 freshman men are given the study habits and attitude survey. Scores range between 0 and 200. So we have our women average and SD, men average and SD, and let's go ahead and write in our sample sizes here too. So sample size for women was 100, sample size for men was 81. So let's test the hypothesis that there is no difference between the men and women for the survey. State the null and alternative hypothesis, compute the test statistic and p-value, and state your conclusion. And let's just assume here that they are random groups. It doesn't say for sure. And so in real life, I might be slightly skeptical about doing this, but for this class, let's go ahead and assume that they are random groups. Also notice both my sample sizes are big, so I can go ahead and do this test. First step, come up with your null and alternative hypotheses. So the null would be that the average for all men is the same as the average for all women. Technically, this would be for all freshman men and all freshman women. Since those are the only people in the study, we can only generalize it to freshmen still. The alternative, let's see, we want to see, just test the hypothesis that there's no difference. So it doesn't say which one they think is higher, they're just wondering if they are different. So, the average for all freshmen men and women is not the same. Or are not, since I did averages. So the averages for all the freshmen men and all the freshman women are not the same. We don't know which one we think is higher, we're just saying not the same. Let's find our standard errors now. So let's do standard error for women first. So that would be our SD over square root of the sample size. So the SD for women is 28 and their sample size is 100. So 28 over the square root of 100 is 2.8. And let's do standard error for the men. So their SD is 35 and divide by the square root of their sample size of 81. So 3.89. Now Z is equal to our sample average for women minus the sample average for men over the square root, and we're going to square each of their standard errors and add them together. So this is going to give me 120 minus 105 over the square root of 2.8 squared plus 3.89 squared. So I get a test statistic of Z equals 3.13. Now your p-value, because you're just wondering, the alternative is just that the averages are not the same and you're not hypothesizing which one is higher, then the p-value is the area in both tails. So what we're going to do is say, okay, here is Z equals 3.13. Here is Z equals negative 3.13, and we want to find the area in both tails. So if I look up negative 3.13 on my normal table, the closest would be this negative 3.15. So the area to the left is 0.0816. And that means the area in the right tail, due to symmetry, is also 0.0816. So my total p-value is 0.0816 plus 0.0816, which is 0.1632%. Once again, we had to add our two p-values together, or not the two p-values, the two areas together to get our p-value. So this is a small p-value, so we will reject the null hypothesis. So we have evidence that the average for all the freshman men is different than the average for all the freshman women. Now notice this doesn't actually tell us which one is higher, if it's the woman higher or the men higher. All that it's telling us is that, yes, they are different. So once again, when we do the two-tailed test, all we can say is whether or not the population averages are equal or different. The test itself doesn't actually say which population average is higher. Now, as a logical person, I could look at it and say, oh, I think that the women are higher. But the test itself does not tell me that. All I asked the test to tell me is if they're different, and it told me, yes, they are different. So example 278, there are 200 subjects in a small clinical trial on vitamin C. Half the subjects are assigned at random to treatment and half to control. Over the period of the treatment groups averaged 2.3 colds and the SD was 3.1. The controls did a little worse, they averaged 2.6 colds and the SD was 2.9. Is the difference in the averages statistically significant? So once again, there is obviously a difference in these sample averages, but we're wondering, is that difference in the sample averages, is that just due to chance error? Or is this evidence that the population averages are also different? So, does vitamin C help prevent colds? That's what we want to answer here. Let's go ahead and write down our information. So, vitamin C, which I'm going to call VC, has, let's see, half of the subjects, there were 200 subjects total, half were treatment, half were control, so that means our sample size equals 100. For the vitamin C, the treatment group, they averaged 2.3 colds, and the SD equals 3.1. For the control group, which I'm just going to call C from now on, they also have a sample size of 100. So both of my sample sizes are large. I can do this test. My average equals 2.6 and the SD equals 2.9. Now for my null hypothesis, it would be that the population averages are the same. Or in other words, vitamin C doesn't help prevent colds. And the alternative is that our population averages, let's start over. The alternative, we want to see if vitamin C helps prevent colds, then they should have less colds. So the average, so the population average for vitamin C should be lower than the population average for the control group. So in other words, vitamin C helps prevent colds. Let's find our standard errors. So let's do the vitamin C first. So once again, it's standard deviation over square root of the sample size. So my SD is 3.1 over the square root of 100. So this gives me 0.31. And the standard error for my control is 2.9 over the square root of 100, so 0.29. Now my test statistic Z is going to be my sample average for vitamin C minus the sample average for the control group. Over the square root, we're going to square each of their standard errors and add them together. So this is going to give me 2.3 minus 2.6 over the square root of 0.31 squared plus 0.29 squared. So negative 0.3 over 0.42. So negative 0.71. Now for my p-value, we have to decide which direction is shade. So we were doing VC minus control. Now, our vitamin C was actually supposed to be lower. We were supposed to have less coals, and so we should actually have small numbers minus big numbers, which should give me negative results. So I should be shading left. So let's see. We're going to shade to the left. Z equals negative 0.71. And that area to the left is 24.2%. So my p-value equals 24.2%. This would be considered a big p-value. It's bigger than 5%. So we fail to reject the null hypothesis. And what this means is we didn't find enough evidence to conclude that vitamin C helps prevent colds. In other words, no evidence that the average for vitamin C was less than the average for the placebo control group. So let's just remind ourselves about what the big and small p-values mean. So when we get a small p-value, that means reject the null, because the null wasn't plausible. We had evidence against the null, which means then that we have evidence for the alternative. Now, if you get a big p-value, we fail to reject the null. What this means is that our null is plausible, believable, so didn't find evidence against the null. And then that means there is no evidence or not enough evidence for the alternative. Now, some people don't like it when I say no evidence because it is all a sliding scale. And so 24% is not enough evidence, 23% is not enough evidence. By the time I get to 6%, we still have not enough evidence. But as soon as I get less than 5%, then we say we have evidence. So no evidence for the alternative or not enough evidence for the alternative. So once again, small p-value means we have evidence for the alternative. Big p-value is not enough evidence for the alternative.